I guess we'll start. So I will continue. I'm sure the rest of you can, the latecomers can pick up on. So let's finish this, our embeddings. So we generated embeddings for also for the documents, the vector. And what can we do with it, right? So we can do cosine similarity, right? So maybe I'll show you a little, those who have not seen cosine similarity. See a Wikipedia on this. Basically, we have two vectors, and maybe let's see a picture what actually we're measuring. Basically, measuring angles. I would like to see a picture here. Let's see a picture here. Right here, right. If we have two-dimensional vector, then of course we can create two angles basically, and we see how close these two vectors are, right? Direction, so to say, which one it is, right? So it turns out technically these cosine similarity is much easier to calculate for a large amount of if you have a large amount of vectors. There's optimizations you can do to calculate quickly if you want to have cosine similarity for everything. That's why it's so widely used. Right, it's not always the right choice, but it's usually a good starting point. So if you have two-dimensional vector, it's easy to visualize. But we, of course, have 50 or 100 vectors. We can't visualize that, but it's still the same thing. We're measuring, so to say, angles of these vectors, basically, and seeing which ones, how close they are. Okay, so that's roughly what it is. Now, how do we find it? Again, we don't have to write the formula ourselves. Scikit-learn has cosine similarity function. We just need to get the embeddings. All right, let's get the first vector. All right, we're gonna print the vector. Right, see what we have. The first document. We'll get all documents, and we will feed all documents. Welcome back. Right. So, and find which document is closest out of all documents. And that document in this particular instance is actually the document itself. Well, which is not surprising because we fed it all documents including itself, right? So the index 0 is the first document, and that's what we are trying to compare it. Obviously, the vectors are same, exactly the same, right? So, but we would like, of course, compare it not only with itself. We want to see, let's say, top 5 most similar documents. So let's do that. Now, we get cosine similarities of all documents related to this particular document, right? I mean, no, this one here, right? So we can get it, but there's the issue here when we get the results is that we don't get back, notice the double brackets, right? So I want to get the top 5 results, but I actually got the first one. So we actually have to go through 0, actually. We need to add it. We need to need to get rid of the top brackets. We have a wrapper around, basically. It's a single dimension, basically, extra wrapper. That often happens, like a little technical detail that sometimes it's easy to miss. Okay, yeah, it's same data, but yeah, there's an extra bracket. That means it's actually two-dimensional, but one extra dimension is, it's just a wrapper, just one item, basically, right? So again, so you see. 163, right? So let's see here, right? We get embeddings, right? These are the top most similar documents. So obviously 0 is the most similar document is the document itself. That's what 0 is, right? But we have at least four documents which are close afterwards. So let's see what they are, right? So those are the index, right? So 450, 76, 264, 112, and of course document itself. Again, we create this doc2vec embedding. Now it's up to us to do the human interpretation, see what is similar about these. So there's a human interpretation factor here, right? A subjective factor. You need to see whether there is some similarities, actually, right? Well, of course, if you check quickly, seems like there's a language in diction, there's certain things which seem similar, right? The shape of the sentence shape looks like there's some way of composing these sentences, these trials, but also the year, right? This is 1720, right? Looks like nothing from the 19th century or 20th century is present. So these, again, maybe there's some certain words there. Also the lengths, we can check the word count. Well, they're all relatively short, right? But you have to do some more. If you are doing the submission of this, it'd be nice to check the actual text of these and see actually what could be similar. Let's compare these two, right? We have a text column, right? Let's do that before we move on. Let's look at let's print out full text of document index 0 and document index, which one? Not 1, but 112. Which is the closest? Let's take a look what, yeah, according to our doc2vec mode, embedding when calculate embedding when we use cosine similarity, right? So let's see what actually does it make sense again. So, or is it completely, maybe the model is just not enough training, maybe not enough data, could be plenty of things. Let's take a look, right? So let's see what we have. Okay, on right, full text on. Right, maybe I'll do some stars. Right, it's not a very big test. Print some stars, I don't know, or something. Yeah, little divider. We'll take a look. Right, full text. Well, actually, I don't think it's full text is correct. Text, right? You see here, Copilot made a mistake. Text, right? Text is a column, not full text, right? I don't have full text column, right? I have text column. Right, so let's try this, see if this works. Yeah, so was indicted for felonious stealing. So yes, there's certain similarities, right? For stealing, structural similarities, right? 40 half-pack loaves. So somebody stole 40 half-pack loaves. That's bread, right? So. All right, so the goods of Sarah Franklin, right? Joe Wicks, yeah, you see appear by, it seems of course the structure of this sentence is very similar. The prisoner been servant. Yes, both cases they are servants, so they actually were working there at whoever they stole it from, right? So there is certainly, the structure looks very similar. So yeah, so it's not, so this seems pretty good actually, right? It did pretty good job. Now, of course, the question is whether, what other works, other documents, you could probably find some other metric by which some other document could be more similar, but this certainly is a good starting point for the further exploration and discussion, subjective human evaluation of these documents, right? So, all right, so things we didn't cover today is there are other embeddings, byte level embedding, byte level tokenization, which is done by ChatGPT and other models, and also other ways of doing word embeddings, which is Glove, which is similar to actually Word2Vec, for example. So there's some references, the GenSim documentation, also here. Now that this all works, let's look at some other things we can do with our data. Now we have our embeddings, meaning we have a document and we have a vector next to it. Let's save it. Embeddings. I'll close it. And now we'll get to some modeling. So We'll start with the simplest model, which, well, it's widely covered. It's something called k-means clustering model. This means we have these 1637 documents. We will cluster them into, say, 10 clusters. So we are going to assume, we'll make some assumptions, that there are 10 different topics, and we'll let the model, the machine learning model, to determine these clusters. This is so-called unsupervised learning, meaning we don't know. We don't have any idea. We don't have any so-called, we don't know what kind of class. We don't have the answers. We don't have any answers whatsoever. Right? We are trying to determine whether there is something similar between different documents. Right? So we are going to cluster them in these sections. So how are we going to do this? We have the 50 or 150 50 elements, 50 values long vector. We use that as our features. We could use something else's features, but that's going to be our starting point. Right. So basically, we have this, imagine 50-dimensional space of dots, right? And we are, and we are trying to see which ones are sort of closed, clustered together, right? Usually in a discussion, maybe I'll show you scikit-learn. Right, scikit-learn. I'll show you two-dimensional space, because we humans think very well in two-dimensional space. We do sort of in 3 dimensions, but 4 or 5 dimensions, no, not so good. We can't really do it. So I'll show you an example of in two-dimensional space. All right. So here, clustering, right? And there's really nice. This picture. I love this picture. This shows you the different algorithms available here, but in general, available in scikit-learn. We can make bigger, open a new tab, we can see a bigger picture. Yeah. So we're going to be using the k-means, actually, not minimal, but just k-means, regular one. And basically, this is two. So this, imagine you have a vector of 2. Just two dot. It only has 2 values. So that's how we can cluster. It works very well if you have a nice clouds, nicely separate. It works pretty well here. However, if you have 2 concentric circles like this, your data, it's not going to work very well. It's probably not what you want. You're probably not going to get anything meaningful here, right, with k-means. You can see immediately the downside of k-means, right? Then something like spectral clustering might be an option. So from this picture, you should see that not the clustering methods, there are many. You might need to try some different ones, actually, and they don't always give you something meaningful, actually. Another thing with k-means is it stands for the k. What does k means? How many clusters, basically. So if you want 3 clusters, you'll get 3 clusters. If you say 10, you'll get 10 clusters. If you say 20, you'll get 20, right? So if you have 1637, of course, you could be very silly. You could say, I want 1637 clusters. You'll get 1637 clusters. Of course, it's not going to be very useful, because you'll just have each document its own cluster, right? So with k-means, you need to decide. You need some other way of deciding how many clusters could be useful. If you have some extra hints of how many possible topics could there be, right? So that might be a very good, any extra information, any metadata about the corpus, it is going to help you tremendously. If you're going completely not knowing what's there, it's going to be a little bit, a lot of trial and error, basically. So, but let's see. Again, k-means it's because it's relatively simple and it's fast. Again, so similarity is basically using the distance. So imagine this space, right? So you say, okay, some dots, you start somewhere. It's a really nifty algorithm. And you sort of say, okay, we have some neighbors, we have some friends to this dot, and we find a new center, and we have these 2 cluster centers, and we keep getting more and more friends to these centers, and we recenter. I'm doing very quick overview of this algorithm, but of course, you don't have to do the algorithm yourself. It's already built in many different language libraries, so widely used. So again, so main point is that there's no right or wrong answer. If you get these clusters, it's exploratory data analysis, right? It can understand the structure. It can find some outliers. That's where it's good. You can find some weird, maybe you find some extra documents which are completely different from other documents, right? So so then it's up to you as a human curator to decide what does this cluster mean? Is this means all the trials for bread, or is it only all the trials of servants, for example, or all the trials of which had a death sentence? It could be something else, right? So k-means. Oh yeah, here's actually a description of the algorithm. Assign the center, recompute again. Sometimes it can fail completely. There's no convergence, meaning it keeps going, right? And there's no center on. It just fails. That's rare. So in practice, again, we don't have to do it. Oh, here's a picture which I mentioned already, right? And let's build a model. Again, so what we'll need? We'll need pandas, of course, again, just to store our data. We'll need to use scikit-learn. We'll use k-means. And again, GenSim, because we'll be using also later on in this session, we'll be using also topic modeling with latent Dirichlet model, and that's going to be a different one. So let's try this. So if you are on the here, let's take a look if this works correctly. Let's open the call up for modeling. Yeah, it looks like, let's connect. Let's see if it loads. Let's see if we can get our pickle data. Let's double check. I'll double check if everything works. Let's see if our pickle works. This is the wrong data. 23. Well, it will work, but let's get 24 actually. Right, it should work. It's the wrong workshop. Right, let's do that. Okay, and let's import it. See if it works. Are we going to be back in business? Yeah, okay, we're back in business. All right, transportation, everything works. All right, now, and let's double check our columns. Yeah, we have 50 values in this row here, right? That's our 50 value vector. That's what we're going to be using as our features. We could use some other things as features as well, by the way, but this is what we're going to use as for start. And let's double check the range of values in a moment, but here I will double change this as well to check the D4. Does it work? Use the D4 because we'll have more data to work with. Yeah, let's do it again. Yeah, we are back in business. Okay, now, so again, before we proceed, I always double check whether everything is okay with these vectors. So let's see the ranges of these values, right? So let's check our first row. See our vector, what are the range of these values? So min and max. So minus 1.17 and 1.5 plus is 1.54, right? So how about all the 1600 vectors? Let's do that. Let's do some stats for that. And let's see, length, min, right, len x, lambda x. So that is actually going to be useless. That's all. Okay, so this means they're all 50-50. So this is basically says all vectors are same size, minimum 50, maximum 50. That's good news, but we want actually, of course, also see what's inside our vectors, right? So we know everything's correct. So now we know what's minimum max. So let's use NumPy. And this is also, so we have a NumPy version. So NumPy is actually what's underneath Pandas, scikit-learn. This is a numerical computing library which is used by pretty much most of the, pretty much anything involving numerical computing is going to use NumPy in Python. But we're going to flatten the list and see what the values are. Okay, yeah, so we're going to flatten the values, and check some statistics on this series. So what I'm going to do is I'm going to take all the vectors, all the 1637 vectors, and I'm going to check what's happening there. Again, this is not required, but just to check what's going on with these data points, right? So I'm going to flatten this series. This is a nice recipe to flatten a list of lists, right? So flatten a list of lists. And have just one big one, right? And so we should have about, this should match this. Let's take a look if that's the case. Indeed, so we have 80,000 something values, right? So everything looks okay. And what our data is, so we see that mean is average is around 0. That's good news. Standard deviation 1.28. Minimum is minus 14. Maximum 17. Right. So let's plot this distribution. I'm going to use a Seaborn. So what Seaborn is a extra add-on library on top of Matplotlib. It's done by somebody else, which makes some has some nice default values. Seaborn comes with Colab. If you don't have it, of course, pip install. If you do not have Seaborn, pip install Seaborn. Let's double check if it actually py.org. Check if it's there. I believe so. Yeah, pip install Seaborn, right? So it's basically Matplotlib interface for some. It provides some sane and nice looking defaults for Matplotlib. Right. So let's do a his plot of that, and it should look pretty nice. Yeah, and this looks quite nice, right? Our data. Again, so what does this represent? This is all the vectors, all our embeddings together in one big list, right? So one big array, and we just saw how the values are distributed. So again, you can see the middle is around 0, right? And how there's some extreme values, right? But this fits very close to standard normal distribution, of course, right? The bell curve. Right, so it looks okay. So that's again, of course, these numbers, where these numbers come from, of course, from the way the embedding works, right? The Word2Vec algorithm, that's what it provides. Okay, so this is just double checking. If we're getting something really different, then you have to see maybe your data is something's not right. Again, usually bell curve, of course, says okay, it looks at least. It does not guarantee that everything is correct, but at least it looks like you're on the right track, right? Of course, not everything is bell curve, of course, but standard distribution appears many places. Okay, but like this is all playing around, just double checking our data. But now we want to build a model. Let's build a model. So k-means. So again, we have a k-means class. We imported. Remember, we imported it from scikit-learn. Where did we import it? Here. Where is it here? Yeah, here we go. You see, from scikit cluster, right? Popular unsupervised clustering algorithm. We only got one k-means, and we here. Oh, here we go. Building. Okay, here we are. Right, building k-means clustering model. Right. So this is the key part. We have decided somewhat arbitrarily that we have 5 topics or 5 different clusters here. For now, also sometimes the starting state, the starting centers might make a difference and it might get stuck. So I'll start with specific centers. Eventually, it should converge to true centers, right? Assuming these 5 clusters exist, right? So the results we will print. We need to prepare some data. So in machine learning, it's extremely common, the features. What's a feature? So we have some row of data. So we need to, the machine learning algorithms will expect some sort of, what's a feature? Data points for each entry, basically, right? So here we have 50 features from our vectors, right? And it's extremely typical to use capital X, right? You could use something else, but it's very typical. You see capital X, this represents multidimensional vector, or basically matrix, basically, right? So generally it's 2D array. So basically it's 2D array, right? So we can check out. So it should be 1637 let's take a look, right? But there might be an issue here. Let's double check. Let's take a look. Right, yeah. First row. Yeah, so this is where it gets slightly tricky, because you would expect it to be n samples, n features, and for some reason we have 1600 entries. We don't have any features, so we'll need to fix it up a little bit. So let's take a look here. Right, so type X is number in the array, right? First value is float. So we need to get to these basically eventually. Right, it's not showing 50 features. Yeah, but let's double check. Why did I? So we need, again, we're going to go to list of lists. And I would like to see why is this actually the dimension. We would expect to see 50 here, right? Let's double check. Why is it not 50? Everything looks correct so far. Maybe we can actually, well, let's do a list. So X list, but actually I would like to see if we can do this. Let's try this without list. Can we do it directly with X, right? Before, right? So before I do this fit with X list. All right, so let's go here and let's try this. So K means, I think it's, yeah, X. I'm just going to do X for now. Let's see what happens now. Yeah, NP array, and now shape, no X converted. Let's try it. Let's see what happens here. We go back and forth. Is there anything different? Converted, type, shape. You see, this is what I wanted. So why didn't it work the first? This is what we want, right? We want 1637 on 50, right? But question is, why didn't it work? Oh, sorry, so what happened here, right? It's a tuple, right? Looks 1600 shape. Why is there no shape? There should be 50. Because this, you see, if I enter the first item, it looks correct, right? Well, let's try the X. So let's try it. See what's happening. I think it's going to yell. The model is going to yell that this is not correct. So X converter should work, right? X list will work, right? Let's try first. Let's try fitting to X. K means to X. It's, yeah, but we'll see. Let's do X. Let's do X for now. It's going to yell. This might throw an error, because it should throw an error because of bad shape. Let's take a look. I think it's going to be an error. Yeah, you see, only length -1 errors can be Python scalars, right? So there's an exception, and exactly it doesn't work. So it seems like we went back and forth and we got what we wanted, right? Yeah, so this is, yeah. So this is a type error, right? So now let's try fitting X list. It's, I mean, now X converter should work. Now let's try fitting to X converted. You generally want, again, you want to work with an NumPy arrays as much as possible. Again, because the list of lists will be slower. Let's try fitting. Yeah, so this should work. Yeah, now it works fine. You see? Can we actually get more data here? Yeah. One more time. Oh, come on. I pressed on this here for some debug information, but now it doesn't look, it's nuts. Okay. Yeah. Now, so yeah, we have fit the model, right? So now what does it mean? We now can find the clusters, right? We'll want to do a cluster. So this will be the fastest. This will also work as well, right? List of lists would be slower. So list of lists would be slower than NumPy array, but it works as well, right? Okay, so we have a model. Now, yeah, we did this here, right? Yeah, we did this here already, so this works. So sometimes one of the takeaways from all of this is that sometimes if something doesn't quite work, you can fall back to your basic structures like dictionaries and list of lists, and when that works, you can go back to something more complex. Right, that's one of the takeaways. Okay, but now let's see, we want to see the results, right? So we can predict, and here we are going to predict on itself, right? So we trained on it. So fit is what builds the model, and predict is now you can fit any type of 50, any type of two-dimensional structure as long as it has 50 values, all right? And you can see, okay, which cluster is going to be in, right? Even if you have some new documents, right? Make prediction. So here we are going to make prediction on ourselves, right? For those who have done some machine learning, think, okay, is that overfitting? No, because we are actually just checking for clustering. We actually need to know where our data lives, right? So this should be xlist. What didn't work? Oh, buffer. Constant double, but got float. Which actually is very close. If you know floats and doubles, they're both floating point values, right? So double is double precision, float is single precision. Let's see what happened here. We try to predict x list. So let's feed x, right? X fixed, right? Yeah, it worked instantly, of course, almost, right? And now it's a series, right? Check on our prediction. First five values of y prediction. Yeah, 1, 1, 1, 1, right? So first 5 documents fall into the same cluster, right? Some random values. Let's do some. Still 1, 1. How about value counts? PD series value counts. What's the prediction of this clustering? We'll get it later. Yeah, we see that interesting enough, the cluster 1 dominates. Cluster 1 dominates about 1400 here already, right? So, but first, before we do more analysis, let's put these values into our data frame, back into the data frame as a prediction, right? We make a cluster. Now, if you go here, we see here that we have our prediction. Again, what does the 1 mean? Well, that's up to you to interpret, right? Could be early 18th century determination. There could be something else, right? But it seems there's heavy, according to this doc2vec embedding, it seems like it's not, the clusters are extremely uneven, right? So that indicates to me that possibly there's not 5 topics or 5 clustering is not really the optimal clustering number, right? That's what it indicates to me. So let's try to see if we can make some more sense of this, right? So yeah, value counts. So value counts is useful. So in pandas, right, you have some column where you can count the values with value counts and see what the distribution is. Get a quick look, right? It should be still the same. Yeah, 1400, 1100, 1400, 1110, 83, and 2 and 1. So these two, again, you would think there would be less, this distribution doesn't look good. So at least you would think 3 clusters would be maybe enough. Yeah, so let's take a look. So let's do some visualizations. What's going on? we are going to group by year and cluster and try to plot, see how the distribution changes of these clusterings changes over years, right? So this operation, this is a pandas, so we're going to group by year and cluster, right? And then size, we're going to unstack, right? Unstack meaning we're going to convert our data in the following form, like this, basically, right? Cluster year and whether it's present. What we see from this operation, something broke. Yeah. Okay. Now, so what's the issue here, right? If you want to plot something, all these nuns, right? We need to fix that before we do anything else. So we're going to replace all the nuns with 0 probably, right? So fill NA is going to replace all of these empty, non-existing values with 0. Again, remember, this is just a temporary data frame we're using for visualization. Sometimes you have to be careful when you put 0 in place of nothing. Maybe 0 is not really a good replacement for nothing, right? And these are two different things. But in this case, for plotting, we'll replace it with nothing. With 0. We'll replace nothing with 0. And then we'll get something like this, right? And now we can plot this. Again, 0, 1, 2, 3, 4 are the clusters, and we see the distribution by years. And again, going back, how did we get this? We grouped by year and cluster. I can maybe show you how this looks like. Maybe I skip some of the part here. Maybe head, I don't know, head 10. Yeah. Not like this. Well, actually, we group by, we need to actually do a, we need to actually aggregation. No, we don't have head, we need to do aggregation size. What happens if we do size? Yeah, we get something like this, right? That's what we got, right? But this is not very useful. So we use unstack, right? We use the one more chain, another command, unstack, right? And so all of these were sort of, we created out of each of these entries, we create a new column for it. So with this recipe, right? So now we can actually visualize this, what's going on. Again, it's hard for humans to make sense. We have a huge table and well, see what's going on. You can see, of course, there's some missing values, but let's look at it, right? Yeah, and maybe also let's do some percentages, maybe. Yeah, so I'll create some new columns for this. We have total 75. See what the percentages are, because also. Why am I doing this? Because different years have different number of documents. So you want to have a proportional representation. Otherwise, you'll have one year has 3,000 trials, one year has 160 trials, right? You want to see the distribution proportionally, right? So for that, I create percentage columns for proportional, for percentage representation of these clusters. Let's see. Total. I don't have total. What's happening? I don't have total column, right? Because I need first credit. So what's a total column? So with this recipe, I'm summing all these columns, right? I could also, of course, instead I could have some specific columns, right? For example. Yeah, something like, well, numeric only, or I could just say maybe if your cluster, new column is maybe, 0, something like this. This would be same thing, 0, 1, 2, 3, 4, right? I could do this, right? But this works. So this example you would see if you need the only specific columns summed, right? Here this sums all of them, all the previous ones, right? So above sums all existing columns, right? For each row. Thank you.
Not the year.
Excuse me? Yeah, year is index. That's index, right? If you see, I could, of course, move that index into a column as well if I needed to, but no. So let me show you what was called the DF year cluster, right? Index, right? You see? That's the index, right? Yeah, so that's another thing to pay attention to. What's an index in Pandas, right? Is it just a number, or it's actually something we have used before, right? So again, for now, why is this year actually called cluster year? Where did that come from? Because we're using here grab by right here and on stack. That's created this. We group by these two columns, right? And that's why the name is automatically created. Of course, we could rename it. So far so good, or something is a little bit. So let's do this. So now here, this didn't work because I didn't have a total column, right? So let's do it over. And I still don't have total column. So what's now? Okay, do I have 0 somewhere? Total. Okay, I didn't run it. Wait a minute, second. Oh, let's do it. Let's do it now. Yeah, okay. Now it should work. Now it worked, and I have my percentage columns, right? Obviously here, if there was, I didn't check for 0 here, right? But obviously all the years I have at least one document, so everything worked out fine, right? It was sort of, it's kind of inevitable. I wouldn't have this year if I didn't have any entries, right? So now I have these percentage representations, and I can plot these, right? Again, I could plot these too, but these would be more useful, right? Full DF. Let's plot it. Yeah, we can see, of course, here this data is so small, we can see all of it, right? I don't remember, this is a sample of the full corpus, a full Bailey corpus, right? So not all years are present. It's only about, I think, 1/100th of a corpus, roughly, right? So I'll use Plotly Express. It's a good starting point with Plotly, right? If you need something fancier, you can adjust it afterwards, right? And I'm going to pick the columns I want to plot, right? Because I'm too lazy to write them by hand, right? Because I have these column names, right? C0 percentage C1 2 4. So I am actually going to just basically use a little small list comprehension to create these column names, right? These are F will use, come on. Yeah, we use columns for plotting. Thank you, Copilot, for picking up on what I'm trying to do. All right. So, and then I'm going to do a bar chart, but it's not going to look good, I think. It's going to look fine. Okay. Yeah. I'm trying to see where is a group. I want to group title. Let's see if this actually works. It should work. Yeah, it does work. All right. So we see some interesting things here. Again, it's much easier if you see a visual representation. We see that year 1784 is just one big cluster, right? So whatever happened in 1884, all the trials according to k-means, embeddings from the doc2vec embeddings, right? It is exactly the same type, right? So, and then we do see some interesting things. We see that certain trials which were not present in 18th century, or very minimum, they appear more and more likely in these follow-up centuries, for example, right? So again, what I don't like about this, of course, is that it's very uneven, right? And there's a couple, like there's single clusters, right? Meaning that is like an outlier. It's somewhere far away from the other ones, basically, right? So, well, maybe there's some corruption, but maybe not. Maybe there's, again, 1784. Maybe there's some unique characteristics. So this would be definitely something to explore separately. What's so special about this 1784? And also, of course, it would make much more sense if you had the full Bailey corpus than you see the other years, right? And then you have much bigger, of course, your visualization would be much bigger. It'd be much easier to see, is everything okay? Here we have this sample, and it's possible it's just too large a gap maybe in our data, right? So, again, this is a how high to jump question. Let's see 3 clusters. So how to determine this number of clusters? There are many approaches. One approach is so-called elbow method, right? Or elbow method, right? We see how percentage of variance increases. Basically, as I mentioned, if you have extreme variation, it would be 1637 clusters. It's pretty much useless. Same as one cluster, also not useless, right? Or either each document is its own thing, or every other document is all, right? So the only question is between 2 and 1636, right? But generally, you want to look at this inflection point, basically, and plot how this how these clustering, how should I say, inertia, I guess, yeah, there's inertia here, how it changes. So basically, since k-means is fast, we can afford to run it multiple times. So basically, we're going to let the computer try different size of clusters, and we'll see, we're going to plot how the distribution of this inertia appears. So I'm going to have a little empty list, right? Inertial values, right? And I'm going to go from, well, 1 is kind of silly, but I'll do 1 for completeness sake. It's, 1 cluster, right? But it works. You can say k-means, give me a 1 cluster model, it will work, right? Pretty silly. Of course, you usually want to start with 2. Usually, yeah. Usually you would want to start with at least, with 2, and go up to 10 or 20, right? 50 is probably too much unless you know something for sure that your data has some 50 different, possibility of 50 different clusters, right? So let's check it out, what we get. So we're going to train our model. We can create actually 20 different models from 1 to 20, right? We can see, right? We have our inertia values, and now we're going to plot them, right? Just do a line plot, right? And see what's happening. Fig line with how many clusters, values, and we have something like this. This does not look too clean. I mean, there's no clear elbow, but again, 3 looks kind of like that, a little bit like that, maybe 6. Right? If you have a completely straight line, you don't know where to stop, right? You're looking for this elbow, basically, right? So 15 maybe, but probably around 3 would be 3 clusters, as we saw from our 5 cluster example. 3 clusters would do just as fine as 5, right? Because we had these 2 one-element clusters, which are basically useless. So of course you have to explore why is there only 1 item, what's so special about that item, right? So we can also do Seaborn, from Seaborn. Yeah. Maybe it's going to look a little nicer. Yeah, same thing, same picture. Let's add grid. Let's add grid. Let's add grid. White grid. White grid, what's going to happen? Yeah, white grid. Okay, yeah. Right, these inertial. Again, so this number of clusters, and that's the inertial values. Again, they're not specifically meaningful. Right, so we do not have a clear, right? So we can choose any number of values. We can play around. Also, right now, you could go to the scikit-learn and say, okay, we tried k-means. We could try other ones. We could try spectral clustering. We could try, well, mean shift perhaps, affinity propagation. Maybe you'll get slightly different results. Again, and thing is, some of these methods, they will try to determine the number of clusters for you, right? You don't have to supply, like in k-means, you have to say how many you have. Here, some of the methods, you don't actually need to worry about it. But of course, as you can see from this 2-dimensional picture, not everything, each will have its own, gotchas, right? Now, so this is something, basically all you have to do is change the import. Basically, instead of k-means, you'd import something else, and everything else would stay the same, roughly the same. You create a new model and assign it to the values you'd assign to the data frame afterwards. Now, if we have time, we'll do one more model, but let's do LDA. This is a different way of modeling, because with the k-means and general all clustering models, we always get one answer. Each document belongs to one category, right? 1, 2, 3, 4. You can say, okay, this is different types, what they are. There's an alternative approach, which is using latent Dirichlet allocation, LDA. It's a softer one, meaning one document can belong to multiple categories, right? Which makes sense, right? You're reading an article about sports, but maybe there's some politics mixed in, maybe there's some religion, I don't know, maybe there's some discussion of food topics, I don't know, right? It can get messy, right? Real life is messy, right? So same goes here. So that's the approach. This is pretty cool. So it's a probabilistic model, right? So the core assumption, did it work out? No, what's broken? It doesn't fit at all? No. All right, maybe when we have after the break, maybe we'll try it, see. During the practical session, I'll come to you, we'll check it out. Well, hopefully LDA will work for you. Let's try LDA. Now, again, obviously, we don't have to implement ourselves because Gensim has already implemented for us. The paper came out in 2004. Of course, Dirichlet lived way before that, but the actual approach came out in 2004 roughly. So what do we need? Again, we need a list of tokens, list of lists. So in this, we have a list of words, right? So again, texts, it wants this, basically. It wants a list of lists. Again, you would think there might be support for NumPy somewhere, but again, we'll stick with list of lists because it works, right? And we'll need to create a dictionary, right? Again, why? Because it's like we need to convert each word to some sort of index, right? A numeric index of what the word is, basically, right? So instead of passing the model, when we're building our model, we're not going to give it, Valdis, BSSD, Riga, and so on. We're going to give it 1, 2, 3, each index for the word, basically, right? So, and let's see what we have. 1800, 118. Okay, so you notice also this dictionary, I think, is slightly different from the one we built earlier in the session. I think maybe a couple hundred words. It's probably you have to check there's some pruning options, maybe what it considers a word. Again, there's some try to keep normal and prune words. Yeah, limit documents. We pass the text, right? So we have our first word. Yeah. So it says appear is first, April, seller, confetti, no, confessed. Confessed. So again, you see all this old English, right? 18th century, right? Confessed, and so on. And you can see last in words, MB, morally, non-combatant, olive, brain, radius, unclaimable, ledger, yeah, very, right, so very interesting words, judging, juries, right. So what's interesting is here, KL, it certainly looks lexicographical, right, to me, right. What seems like there's a huge jump, right, M, what happened to all the U words on M and O, right? So that's something that's interesting. Well, no, you have legally after. No, that's the middle, right? So first and last is fine. Or maybe I missed up here. Oh yeah, but it looks like last, right? That certainly looks like last items. Well, I think it's not ordered, right? It's still probably items. It's probably not ordered, right? Or dictionary. It's a dictionary. It's not it is a dictionary, but it's not a regular Python dictionary, right? So it has some extra things, right? So it's not probably so, but as I would imagine, the order, again, it shouldn't really matter, right? It's just a number. We are assigning a number for each word. It's just curious how it's done, because again, you're skipping B's here, right? AC. I'm sure the ancient, this Bailey corpus has some words with B. Well, let's try. I'm just yeah, I'm just curious, how did the Gensim creators of Gensim, how did they create this mapping? I mean, it doesn't really matter at all. It's just that it seems to have some ordering, but not full ordering, right? Let's see if we can find the words that start with B from this. Let's get all words that start with B from this dictionary. B words. Yeah, you see, Coppold is pretty smart. Look at this here. What I'm impressed about this, it picked up that there is a second value, right? We're going through each item in our dictionary, so the value, right? We're checking whether this starts with B, right? So let's check out how many we can check. Now, let's print first 5. I'm sure there's 5 words, right? Again, it's not going to be, if you have nothing, we'll have nothing, but let's take a look. Yeah, Bermudas, Bishopsgate Street. Yeah, bar, beef. Yeah, so it's not completely ordered. So, well, of course, what another thing could be, I think it's possibly, since Python dictionaries have this property, that the keys, the order of insertions preserved since version 3.6 roughly, right? It used to be there's no guarantee whatsoever, but now if you are adding keys to your dictionary, the order is going to be preserved. So what's happening, my hypothesis, this is just hypothesis, that we have multiple documents, so you add the words from the first document, and that order will be preserved, and if you have any new words, by document, so each document you keep adding new words, basically. That's why it looks ordered, but it's not fully ordered, right? I think it's ordered by each document within. But again, this is just extra exploration to see what's happening. I just want to make sure we have words with B, right? That we certainly do. Yeah. And this also is keyword. This is the same thing we did here, word for word. Or this is also the same thing exactly I did. It's kind of funny. I did this here before. Maybe you could try C, right, and so on. Right. It still works same way. Right. So now we need to create the corpus for Gensim, right, of this. And this will will create a bag of words for this, right? And check here what's happening here. I think you can see it here, right? 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 8, 9. So this hypothesis, I think, certainly has some ground. Look at this here. So first word, second word. Here we have different index because that's second document, and some words are present from the first document, but other ones are appeared for first time, so they get a new index, basically. Right? Yeah, that's what it looks like. So first one should have 46 here, right? Maybe it didn't do 47 because it didn't prune the 3 words, right? The 3 short ones, right? This one is a little bit more, again, a little bit. Maybe we might have wanted to clean the extra 3 words before, right? That's why it pays to pay attention to what we are doing, the lengths. See actually if there's some mismatch, right? Okay. So for our purpose, it doesn't matter. So yeah. So what's word 1, right? We'll get it afterwards, right? So now to create this model, we're going to import the LDA model on our corpus. Our corpus is basically a collection of tuples, right? It's a list of tuples, basically, or a list of list of tuples. So each document is represented by a list of tuples, basically. And that's what why do we need this? Because that's what LDA model expects, right? Of course, it's important for us not to lose this indexing. I mean, I could feed any number of tuples and the LDA model will work on it, right? But obviously, eventually we want to get back these numbers, right? So that's why we're using the built-in these methods, right? And there's no need to reinvent your own methods for this. So, and again here, similarly to k-means, we have number of topics. So we decide that we might have 10 topics. On LDA, we'll try to create these 10 topics, right? We will match these documents and go through by assigning, creating probabilities that each document stands in some topic. Well, let's take a look. Okay, what happened here? Oh, because the corpus, we don't have corpus. Oh, I guess I do need corpus. Yeah, I have corpus now. Again, so corpus is what? So corpus, so data type. So data type of corpus is list of tuples. Thank you, Copilot. Very smart. It figured out what we have, right? List of tuples, right? So each tuple contains word ID and count of that word in a document. Okay, not count, but presence, I would say. I don't think there's, I think we don't have repeats, right? No, it does have count. Yeah, it does have count. Yeah, it does have, this has counts. This has counts. Yeah, there's count here too, right? Correct? Right? So, right? So hopefully everyone's clear what we are feeding in, right? The model. Okay. So now it should work. Topics, ID to word, right? Again, since we created dictionary separately, we're gonna give it so we can get back the actual words, right? So if you feed in the wrong direction, you won't be able to tell what the word is, right? So let's say, now it's gonna train. This might take, how long it take before? I didn't check. Oh, 8 seconds, not too bad, right? Again, it's pretty fast. Again, we have small corpus. And now we have topics, right? And they might seem silly, but look at this topic. So basically, it will present keywords, right, and how important they are. And notice we didn't clean this. We fed in, we didn't get rid of stop words. There's a mister. There's some go. I say there's a lot of things we should probably get rid of first before we create this model. That would be something you might want to do, right? Just rerun this, but without these extra stop words, right? Because I think prisoner might be important, but it's of course should be probably present mostly in many texts. But that might be something you can definitely divide. But do or go most likely is not gonna be very well. Could be. Right, house. Well, you see, house, that seems important. It could be important. Right, so, right, man, no, these are lemmas. These are working with lemmas, right? So, tell, fine. You could, of course, try it working with just the actual text, with a form, maybe with stems. But first, since assume everything works, let's do and save, right? This is a helper utility to create a path. I'm going to save this, right? Data path. You can actually do it without this, I believe. You can just do it directly, right? You need this actually. So where did it save? Let's take a look. Did it save in our current directory? I didn't check. LDA model 10, that's and any name you want, right? So any relevant, any appropriate name would do, right? And where is our model saved? Notebooks? I believe it's in notebooks here, right? Yeah, here it is. No, that's topics. LDA model. Did I save it actually? No, I saved it. Good question. Where did I save it? Or maybe in temp? Test. It says test. Really? Test? I don't see this here. Or maybe in temp. We can, of course, check, right? Where is it saved? Topics. I see. Yes. So this, I think, I would probably just save it. I'll skip this part here. I think, I'll do this actually, right? I will do this instead. Models folder, right? That's what I usually do, right? On save pass models, right? and save it into temp file. Would be temp file. Yeah, temp file equals what? Past models, LDA model 10. That makes more sense, right? And now it should work in proper, right? But models, do you want them here? Probably separately. Let's do it in a one level up, right? In our parent directory. Yeah. Let's do that. So that creates a models folder if it does not exist, right? And then we say, okay, well again, let's do it correctly. And of course, obviously, if you have models folder, you don't need this, but it doesn't hurt. But this one, should match, right? Let's try. Nope. Okay, what did we do wrong? File must have a right attribute. Okay, let's see, what did we do wrong? That's why maybe it has some specific Windows path. I know what. Yes, okay. So this was the thing which kind of annoyed me with GenSim, that it was written before pass, so it does not know about the pass methods. So what do you need? You need to convert it back to string, right? So GenSim is not pass aware, so you need to convert. Yeah, okay, so temp file, right? I'm just fail. Fail, yeah, equals string. It's very easy to do. You just convert typecast to string, right? Again, this is one of those things with quality of life, right? You have to know a little bit about Python just to see what the error is, and you see it should work. Yeah, now it should work, and I have nice looking models folder. Looks like the material design guy also knows that there's such thing as models, right? I don't know what kind of model, but so how is it saved? Actually, it actually saves 4 different files. But when you load it, you just need the name, right? So now you can load it anytime you need, right? You can load it, you can train it. Of course, this is crucial. If you're going to be training it, if you have a larger corpus, you spend half a day training, and you don't want to do it again, right? So you want to load the model from existing, right? And then you want to do your inference afterwards. So now we can load. If you want to, of course, we don't need to load it again, but we can. It should work, right? Yeah. And now we can print the topics from it should be the same. Okay, so yeah, the prisoner, right? Okay. Now, shape, right? Topic array, 10. Right? Now, show topics. Yeah. Now, yeah, but and we got all the prison words as well, right? Looks like prison is always somewhere there. Well, kind of obvious. So a very interesting library to visualize these results is something called PyLDA Viz, which stands for visualization. And this does make these results quite more palatable, more approachable. I like this library. So PyLDA Viz. Let me show you where, if you don't have it, you import it. Yeah. If you do not have it, use pip, install PyLDS. Let's double check link on PyPy. Oh. Let's check. Is this correct link? Let's double check. Yeah, 3.41. April 24 last year, right? And it makes these nice looking HTML-based, web page-based visualizations. It actually comes from our package, but it makes it easier to interpret what was this model doing, right? Maybe it's complete nonsense, right? So let's run it. Let's import it. If you don't have it, again, the question is, does Colab use it? Does Colab have it? I don't know. You might need to import it, right? Does Colab have this? Anyone on Colab? You all have local ones, right? So now we are going to, it's easy to do. So you have the model, right? You have the corpus and you have the dictionary. And that's it. So that's why it's so nice to use, assuming you already have your model, you have your corpus, and you have the dictionary. it's going to be, you prepare it, and then you prepare it for a while, and you can display it directly on a notebook, but generally I save it separately. Let's look, see if it actually displays here. I don't know if it's going to work. Yeah, it works, right? But this, of course, it's we have nice interactive visualization, but I have an extra Visual Studio Code, right? But let's do it separately. Let's save it. LDA data, right? We're going to save it as HTML. I'll save it actually, well, I could probably use notebooks or HTML folder. Maybe I should have made an HTML model. I saved it here and directly here, right? So it's, let's double check if that's the case. So I saved it just right now, 310. Yeah, so that looks like I have a new visualization. So I'll use Chrome or Safari or Firefox, and you should be able to see this here, right? Yeah, there we go. So you have 10 topics, right? You see there's, of course, some overlap, right? And you see this visualization, what's going on? Remember, we have how many, what's the size of vector for each document? 50, right? So what happened here? How does it show it in 2 dimensions? Well, it's using something called PCA. Let me see. Primary component analysis, as it was. Let's see if we did it correctly. All right. So PCA, yeah, I believe so. It stands for principal component analysis. Yeah. So what's happening is basically you have this 50 for each vector, but it squeezes into 2 dimensions basically, right? Obviously losing some data in the process, but this makes typically used for showing results because now you can see 2 dimensions, right? Easily, right? But technically each of these PC1 and PC2 was created from these 50. From 50 went down to 2 basically, right? So, but you can see this nicely, each topic, and you can see the most relevant terms for this, right? So this certainly needs to do some extra work to clean up because there's too many stop words. Again, I would probably get rid of many stop words, right? You can see say, do, prisoner, right? It's almost always present, right? You can see here. It's like almost hard to find which doesn't have prisoners say Mr., right? So because you want to have some of the uniques actually, right? So there's S, which is probably the shillings as mentioned before, right? So guilty, well, some have, well, thing is some things maybe there's guilty. Some things don't have guilt, right? So there's a couple of things which are different, right? So again, I personally would say this needs the say probably needs to go. The stop words will need to be removed. This shows why stop words generally kind of don't help, right? Maybe you can come up with explanation why which ones would be still useful, right? But still I think is relevant, right? But say is certainly not relevant here, right? They're all going to say something, right? So all right. So the question is now for you, technical question. Were you able to run PyLDA viz? Nope. Yes. Yes. How many? Raise your hands who were able to run it. 1, 2. How about others? It works for you in the back, right? Work? No, Vestos? No, artists? No. How about you guys? Worked? Okay, great. Right. So you did have to install. So we can try to see what happens in Copilot, right? I mean, it's not Copilot, in Colab, right? If you try to do it in a Colab, right? I don't think PyLDA. Here's a trick, right? You might need to run. If you install it, you might need to rerun the notebook. I don't know. It might not pick up. So PyLDA. I have connect. Okay. We go to here. So let's see if this happens here. Is this going to work? I don't think it's going to work. Yeah, module not found error. So what do you do in Colab? I'll show you. So if you don't have this. So you do this pip install PyLDA viz, right? Oh, there you go. It should work. Yeah, it installs. You see, it checks for Gensim, it checks for scikit-learn, checks for pandas. We have all that, but it still needs to install PyLDA itself, right? Because it's a helper library, right? Now we installed it, but I'll show you that here's a trick with Colab. You want to import it. Oh, it works actually. Oh, it worked instantly. Okay. Sometimes when you import something in Colab, you need to restart it and then run it, right? Here, it's already available, right? So maybe a link if you don't have it. Yeah. Or in notebook, use such as, yeah, from command line, right? Okay, so those are instructions if you don't have this library yet. Now, what else do we have here? So we've done LDA. So next steps would be maybe get rid of, like I mentioned, get rid of short words, maybe different number of topics. Maybe also see if there's also a different type of embeddings, because we're using simple frequency analysis right here for LDA. Maybe there's other way of feeding it, LDA model different, not just bag of words, basically. That's another thing to maybe explore. All right, so that concludes our modeling session. What I would like to check before we start doing yourself some works, let's look at another. Okay, here's models. That's good. Day 2, models. This will be short for the visualization. We've seen be using Plotly. We've been using Matplotlib, Seaborn. We saw PyLDA viz. There's an interesting, very little known library called scattertext, right? If you have two corpora to compare, you need a visualization. This is pretty nice, right? Again, this is not for everything, but for if you want to compare two different corpora, this might be pretty nice, right? I don't use this library often, but if you need to, this might be a good option. This is this part, day 2, part 2, right? So you'd install this install scattertext, right? And we are going to create scattertext as st. So alias for scattertext, right, is st. On we're going to use a different corpora for this, right? This was for, well, a topic of interest right now, of course, politics, convention data from 2012, right? No problem need convention data 2024, right, in America right now in a few days, right? But so basically we are going to create some data. And for different parties, we have, of course, only two parties, so it's kind of nice to compare, right? And produce some results. Let's take a look what's happening here. This is an example. And then we will see, if we have a few minutes, maybe we'll see if we can do it ourselves. I think it worked. Yes. Oh, I forgot to go to IP progress. Yeah. Yeah, I need to upload this. This make a nice progress update. Somewhere here I should have done it. Oh, I thought I did. Yeah. There's the work. Okay. So now the question is, we have our data shape and we have our party, text, speaker, parse, right? So Democrats, Barack Obama, Michelle Obama, and Joe Biden, right? Pretty interesting corpus, of course, right? And see if we can visualize this, right? And so basically we have scatter, we need to, each column, right, needs to be in this scatter paste NLP doc format, right? So we'll see if we can do this for our own corpus, something like that, right? But I want to see the visualization actually here. Can we, let's do this line here. And we're going to write HTML for this. See this works, encoding UF8. Let's see this work. Okay, apparently it did work. Yeah, it did work. So here we have it. Revealing file on. Let's see what it looks like. All right. Serge saw it should come up. It's pretty big visualization. Take a while to load, even locally. Oh, there you have to click on search. Okay, yeah. So you see Democrats and Republicans, right? That's a perfect way for, for comparing two corpora, right? So you can see which issues are important for one corpora on another one, right? Democratic frequent, right? Obama, of course, president. Republicans want the government and business and better, right? So you have two way of signing two values, right? Then this is a nice library, right? It gives you can check the words, right? You can also click on say Obamacare, right? And you can see the examples of this, right? Right. So this is pretty nice. So how could we get it for our own? We have a few minutes to do it, and we can do it, right? So basically, we need a category, right? They had Democrats and on Republicans. We do something like that. But also the issue is, of course, they need this scatter text whitespace doc format for the actual documents, right? So we read our Old Bailey sample from 24. And so for now, I think I'll do punishment, right? So what I did is I took either going free, compare the documents which the defendant went free and the ones where it didn't go free, basically, right? So sort of, again, binary, right? So we have, but the only problem is we have 275 unique punishments, right? But of course, they overlap, right? That's too much, right? If you lowercase, right? Well, there's 85 punishments involving death, right? Whip, there's 29 whippings, and so on, right? And the prison, 57, right? So let's check with different punishments. We can do some punishment counts, right? Empty. So we can see the empty death, whip, prison, transportation, fine, or discharge. But empty is the one where you go free, right? So for now, we'll need to group all of these together into one category: punishment and non-punishment, basically, right? And you can see this is, yes, actually, good point. Good point. You see, good catch, actually. So sometimes discharge means go free. Very good point, actually, right? So you can see sometimes this category, this goes back to our first day, how we determine the punishment category, because there's a text field. It's kind of open-ended, a very common issue when working with documents, right? Yeah, so this is up to you to make this, to put together under one umbrella. There's 7 years penal servitude, there's 6 years, 5 years, right? I don't know what it means, 18 months imprisonment, second division. So this must be some sort of like, I don't know, country club prison, I don't know. But, right, so basically we want to squeeze all this into categories. So we'll see if I picked up on this discharge, actually, right? So mine was, right, ugly cut, if strip is none, or text strip. Return empty, right? So I think I'll need to modify this. Or discharge, right? I think I'll need to modify this function, right? Or a little bit of a calc here, punishment string is none. sometimes or. Also, what I'll do is also if punishment contains discharge, also return empty. So, if discharge and punishment text lower, return empty again, right? And this one is unknown. Oh, forward, okay. Right. So, it should be forward, okay. Discharge, so this should be okay. Let's take a look on unknown. Now we are going to get it out. So punishment type is apply. Right. So punish type transport, transport, transport. Now we need to convert it into this each text, right? To this Sakadar text white space NLP with sentences, right? Basically, we need to create it. So parse category, parse here. Well, let's see how quickly it works. So for each text, we need to use this white space method. And we have it. And again, punishment types. We have transport, empty, death, unknown, whip, wine, prison. Okay, right. So now we are getting closer. And we're going to do freedom. Right. Oh, I was using, no, it's all correct. Empty, yeah. So freedom category. Yeah, I did pick up on discharge before, so we're not missing that. Now, freedom is punishment 0, freedom 1. Again, of course, up to us. And now we're going to build the corpus. Before we take the break. Create a new data frame. And let's see, now we need to know which columns to do. So, to create the HTML, we pass in a corpus, category freedom, right? Not category name punishment, right? Category name freedom, freedom punishment, at least 0 terms, right? On the size, metadata. And we are also going to open up and write this file into data folder. Let's take a look what happens. Did I mess up anywhere? It looks like we can check or find with freedom. And it's a pretty big file. You see this is going to be big visualization, about 7 megabytes. Well, these days 7 megabyte web page is nothing big. And let's check what it looks like. It's still okay. So, freedom and punishment categories. So we can see what's common, So, acquitted obviously is part of the freedom. Captains apparently for some reason get acquitted. I don't know why. Age, brother, this handkerchief, right? Apparently that is a serious offense. It seems like you get punished. Let's check it out. Right. So, punishment 11 times. Let's see. Yeah, so if you get handkerchief, actually you get, steal. Because why? This is an interesting discussion about this. What's the story with this? This actually was serious business in the 18th century because they were expensive to make or they were handmade, obviously. And actually, it was a serious offense to steal somebody's handkerchiefs, right? Of laundry, for example, right? Value 10 pennies, right? That's a couple dollars at least, couple euros these days, right? Linen, right? But this is actually freedom. But here mostly, right? You drop something, 1 line and country, yes. This is kind of amazing. This is one of the takeaways from exploring this corpus. Yeah, that this stealing, silk or even linen handkerchief was a serious offense. Right. Right. You can see the stories. Right. Yes. Okay, but let's take a break for about 10 minutes, and then we can try doing it ourselves. Something, I'll save this. It's, visualization. And we can check what is top freedom. I don't know what's happening with Mackenzie or captain. Let's check the captain. Yeah, captains go more free. Captain Spurl, I was Captain Spurls, captains. Yeah, this is a big story with captain. There's a huge trial. Captain Mackenzie. That, yes, it goes together. There's one big trial apparently. Yeah. Maybe that's the one. No, that was death. The 10,000 one was death. Right. You might want to actually, that would be an idea to explore what happened in that long story with the big 10,000 one. Okay, so let's take a break for 10 minutes. All right, I guess we can start exploring this visualization. Before, actually, I would like to talk about, of course, well, I guess I'll wait till everybody gets back, actually, since I want to talk about our assignment, actually, what I would like to see. And so, let me load it up. Okay, a few more people coming back. Welcome back. All right, so welcome back. Internet, okay, everything works. Now, let's talk about our final the part of the session, final session, and this is the part where you do some work, your chance to shine, and basically I'm going to provide you with a notebook. Right? The assignment is basically to do some cleaning, and hopefully you get to embeddings for the corpus of your choice. Modeling part, this would be probably too much. Do it in just in this session. Maybe if you have time, you can do it, or do it in the evening. But better would be to, of course, to submit during this session, right? So let's check our Google form if it's correct. I want to check if it's correct. Link. Yeah, this one here, I think it's the current one. Yes, BSSDH 24, right? So again, this is for those who want credit. If you don't need credit, of course, you can submit, right? Here, right? For my course, remember for credit you need 2 out of 5, right? 2 out of 5, and there's so you have 1, 2, 3, 4 of them, right? Actually, so 2 out of 4, I guess. 2 out of 4, I guess, right? 2 out of 4. Right, submissions. So what do I want to see is basically that you loaded some corpus. I mean, this could be also this Bailey, but then if I use this existing corpus we used for this workshop, I would like to see some more, maybe some new column, maybe the defendant column, or maybe gender of the defendant, things like that would be interesting to see. For example, some extra extraction, for example. And I would like to see embeddings. Again, you can do a bag of words embedding, or something like TF-IDF, or maybe, word-to-vec embedding, right? So, any library. And also, I would like to see a top 5 words for each document, right? And it's completely up to you how you define top, right? Some ideas. So that's all that's asked of you. It's pretty open-ended, right? So there's not going to be like one impossible, submission. I'm not going to as long as I see you loaded the corpus and you did some work on it, it's going to be accepted, right? So don't worry if you don't complete all the steps, right? So this applies to the Zoom session as well. I would like to see you load some corpora, do some cleaning, right? And hopefully create the embeddings. And if you get to some modeling, that'd be great. But so that's a requirement. That's an assignment. During the class, if you have any technical issues, I'll be coming around, see if I can help you with any issues. If you need a problem with some libraries, maybe, because welcome back, right? I'm talking about the assignment. If you need the credit for this course, there's a part 3 of the student of the workbook, right? I just opened up in the Colab. Also opened up in Visual Studio Code, right? So there's a link to Google Forms, right? And you can submit it there, right? The limit is, I think, 10 megabytes. So if you have something really extensive, you might need to provide some links to the other external data source, maybe, right? But 10 megabytes should be enough for this course. And of course, if you're not taking this course for credit, you can submit your own notebook just to submit it, basically. So I will look at it, or one of our assistants will look at it, and that this will be appreciated, right? So now, where do you get the data? You probably have some of your own data sets, right? So again, you don't have to submit the full data set. I just want to see your work on the notebook, right? Especially if it's a large data set, you don't have to submit the data. Just want to see the link, right, where you got the data, assuming it's open data set, right? There are lots of different data sets. Project Gutenberg is good, Kaggle, also public data sets. There's also European data set, Latvian one. Let me show you also a European one. Let me add this one. European Open Data Portal. I think this is correct. Let's double check. Of course, we already mentioned Clarin. Yeah, offshore European data. There's 1 million, almost 2 million data sets, right? Again, the main issue will be that sometimes the data will be in JSON, sometimes it will be XML. It will not be in a nice, tidy, data frame format. It could be CSV. So for this workshop, if you take a CSV dataset, it will be easier to work with, of course. You can skip many steps, right? Also Clarin datasets, right? Also would be, so data here also would be a good dataset, good repository, right? Resource for Polish content, Finland, all records from language of Finland, right? So this is definitely a good starting point as well. And provided from the examples from yesterday, you should be able to download them with provide the URL and download. Clarin, let's see how is. Yes, and I will. Yeah, all right. No. Yeah. So what I want to see is some embeddings. Again, it could be any type of embedding, right? Some sort of numerical the representation of your text data. If you think about it, you can say, okay, if you want to be really lazy, I mean, length of words is technically also an embedding. It's not usually not enough for doing anything useful. But if you say, okay, my document is 67 words long, that's technically an embedding, right? It's just one single item, with not much to go on. But of course, this length could be sometimes used as an extra feature, for example, right? Technically, I should mention this, right? So yeah, the top 5 words for each document. So this is also, I think, an interesting approach, right? What's top 5 words, right? Could be just frequency, could be TF-IDF, right? It could be some other thing, right? Top 5 words for each document, right? Now, it's pretty open-ended, right? I just want to see if you did some work. When you submit this notebook, right? Maybe have your name up top, right? That your name goes here, right? I'll do that. Your name here. Yeah, so I see who submitted, just in case, you know, I don't see the, I don't see your, I mean, the Google Forms will show to me, will show where it came from, but it's a good idea to have it just in case. So let's see what's happening here. Updated student work. There is some issue with GitHub. Oh, it worked. Okay, good. Let's double check. Did it work? Yeah, it worked. So we can double check whether the new changes went through. Yeah. Again, if you're on call-up, those who don't have local installation, what you do is you do some work, you download the IPNB, and then you upload it to Google Forms. That's the easiest workflow. I mean, you could of course copy somewhere else, but that I think is the easiest one to work remotely. Yeah, it'd be interesting to play around with this. So how much help you get with? I'll try to do this with maybe like experiment, see how much work you can do without with this Google assistant, basically, right? Connecting. Let's see what we can do with this, right? See how well it works. I'm just going to play around with this. Can we do anything with this, or not? Where are my AI tooling? Oh, there we go. Terminal, command palette, code snippets. Where's my code? Oh, here you go. Right. Let's get some. Let's get some data from Clarin. Right. I don't think it's going to work because this is a. Let's import needed Python libraries and download the data. Let's find a Clarin. I'll give you an example. Maybe this can be fun exercise. Let's go for speech signals. No, I don't want speech signals. Brain humanities. We'll do Estonian language. Any Estonians here? No. So I'll do Estonian language resource, right? Something here which I don't have any knowledge. Let's take a visit portal. But yeah, you see it goes actually to the Estonian. So if you go to Latvian, Clarin is just a starting point. So this is something I have have very little knowledge of. Well, of course, Estonian is completely different from Latvian. Not even the same what's it called? Family, yes. It's Finno-Ugrish, right? What's called, and we are, of course, Indo, what's called? Indo, yeah. So let's see what kind of corpora we can find, right? So I will provide historical concordance. No, Valency corpus. I want some plain text. Okay, and this has some answer. That's really nice. Valency corpus, how big is it? Well, unfortunately, I need to translate to Google Translate. Oh, it's CSV. I like that. On actually download. Okay, so the link. Let's see what happens. It actually download this. How big is it? Yeah, not too big. So I will see what AI can do. Right. So of course I need to know the link. Not that one. URL. The result as CSV file. Then load the CSV file into data frame. Let's see what happens. Let's see how well AI from Google gets with this task. Hopefully, right? Yeah, and I didn't write correct. Okay. He only offers one version. So URL requests pandas. It writes and reads. Looks okay to me so far. Nothing too special, right? We'll see if this actually works. The only question is this going to work, right? I have response content. Okay, it should work. Yeah, it should work. Let's take a look on. But now, of course, the problem is Colab. Of course, I'm so used to Copilot that I have to do this myself. So head, right? I have to do this df head, right? All right. So let's take a look what happens. Yeah, let's see. Oh yeah, it worked on first try. All right. So very good. So you have valence, right? So now you have this. All left to do is to generate some embeddings out of these paragraphs, right? So this is from an Estonian newspaper, and there's some already, you could use this for classified work with classification, for training some model in Estonian language, right? Or you could also use for clustering, but again, now, next steps, right now, so we have df, let's generate embeddings. Now, let's see, next steps. What is this scene? Okay, using data from create bag of word embedding for a paragraph column. Let's see what happens. It's not a very. I'm curious how well Google Gemini works. It's pretty decent. I mean, Gemini is good. Actually, I'm actually still paying for Gemini. I have not canceled yet my subscription, so I don't use it much. I use mostly APIs, so it's not bad. But let's see how this one works. Embedding for paragraph, and save it into embedding column. Okay. In the data frame. Again, I'm giving very vague instruction for paragraph column. Let's see this instruction, is this going to work or not? All right. So, count vectorizer, yeah, it certainly looks decent enough, right? List, okay, so what happened this? We're going to look like NumPy array. This is very similar to what we did in the class, right? So we load the count vectorizer, initialize count vectorizer, embeddings, right? So I'm doing all your classwork for you guys, right? So, and this gets you bag of words vectorizer, right? Not too hard, right? Paragraph, right? It looks okay. So notice embeddings. This is a little bit iffy. Do we really need to do this? List and embeddings. I kind of maybe we can skip this part here. I don't know. We'll try this again. Remember, that's why I don't like this approach, because you don't have this instant access. You have to sort of like run it, and then you have to see if it worked correctly. Now, let's see head. Let's see what happens. I'm not 100% sure this will work, but it might work. Yeah, it worked. So 0, 0, 0, 0. So this is a full. Yeah, this is a full unsparse array, right? It's a full array. So let's see how big is this. Let's double check the shape of this, right? Let's check again. Let's check shape of. Well, I guess I'll have to generate this again because I'm lazy. Let's see. This is. Yeah. Okay, show size of embedding column, shape. Okay, have to. Yeah, apply to sum. And the question is, why does this does nothing? Right, this is not in place, this does nothing, it's not shown anywhere, right? So again, but this one, bytes, lambda x, embedding, apply lambda x lambda bytes, sum. I think it's a little bit redundant, okay, but I guess it will work side of embedding column. I don't want the bytes, you see, show. minimum and max number of elements in embedding column. But you see that okay, I'll do it again maybe. I guess, how can I do it over again? The prompt, I guess I'll regenerate here. Let's see how this works. So, show minimum and maximum number of elements in embedding column. Column cells. I guess maybe something like that. Maybe this will be better. Minimum, and minimum, okay. Minimum. Yeah, embedding length, apply length, yeah. Let's see, this should work. Yeah, so 32,856. So yeah, so basically what we did is, I mean, it's an embedding, it's a legal embedding, it's 32,000 long, right? It's full length, but it's pretty hard to work with this type of embedding because it's too long actually, right? 32,000 long vector, and it's mostly zeros, right? It's extremely sparse, right? But it works, right? It's actually this. If you got this far, I would accept it as a solution, as a valid assignment. But of course, if you have time, it would be nice to see some extra work here done here, right? So simple one. This would be nice to compare it to squeeze down to maybe use a smaller number of items, maybe, right? So also we haven't checked. Let's check. Find most frequent occurrence of I can spell occurrence in embedding column vectors, right? Actually, I want to see, right? So the question is this: find what values are present in embedding column of DF. Let's see what happens. Right. So all values, well, it's certainly a solution, not a horrible solution, but of course this is not a pandas. It's sort of like you have a set and you keep adding values. Well, for value in embedding, let's take a look what happens here. But we want to actually, for embedding in DF embedding, I don't like the loops here for embedding in DF embedding. This is not a very good solution actually, but we can run it. It's not going to be good because looping is not good for value and embedding. Yeah, it's going to take a while. So that's a danger with running using AI assistants, is that you can end up with a relatively bad solution if you're not aware of how pandas works. It's just going to be slow, right? We will get. Yeah, okay, unique values, okay. So what do we know from this? So it certainly looks like, yeah, up to 11. So it looks like no more than 11 occurrence of any word. That's kind of interesting, right? All right. What I'll do is, I will save this, and I'll run it on my local notebook and see if I can do a quicker analysis, because this is not a good practice. There should be a more pandas-centric way, because what we're doing here, we're looping through each item in a pandas and then adding for each value and embedding. So that's what. First of all, how many documents we have, right? How many documents do we have? I didn't even check. Shape of DF. I didn't check actually. Come on. 4,000, not too big, that's fine, right? Let me save this. I'm going to show you how you can, if you're logged into your GitHub, you can save a copy GitHub directly like this. But maybe I'll stop talking. I'll let you guys work. sorry, we'll finish in a moment. Yeah. So guys, I guess technically we are done for today, I understand, but again, if you have time, today you can continue, you can submit now or you can submit later today. So any questions? Are you guys able to follow most of the material? Some knowledge. So thank you everyone. All right.